Dear experts and evening. My name is Zhang Sheng. I am a master student studying in the engineering and Three Gorges University. I would like to thank the organizing committee for giving me this opportunity to communicate and study with you. My presentation is about effect of clay fraction and mechanical behaviors of waste rock fine-based brick. I will report from the following 5 parts. First one, research background. We found in occurring in Yichang, Hubei province that a large amount of waste rock fine and water mixture were produced in the process of rock milling, which was in the form of slurry. Because there was no proper disposal method, these rock fine were piled up in the open air, occupying a large at the same time, affected by rain, a large amount of rock fine moved with water, causing pollution to nearby water sources. And some rock fine was washed by water, damaging farmland. Therefore, the problem of waste rock fine needs to be solved urgently. On the other hand, a large number of phosphogypsum in Yichang need to be treated every year. This reminds us whether there is a suitable solution to treat these two kinds of waste at the same time. On the one hand, we can tap the potential value of waste, and on the other hand, we can achieve the goal of treating waste with waste. Next, I will introduce the current existing solutions of waste rock fine. The methods for the resource utilization of solid wastes, such as waste rock fine, are mainly divided into the following 4 kinds. One is to be used as road bed filling materials. The second is to prepare lightweight aggregate. And the third is to prepare high-strength aggregate. The last place natural fine aggregate to prepare non-sintering block, which is also the ultimate goal of our study. This method not only effectively reduces the carbon emissions in the process of raw material preparation, but also fully excavates the potential value of waste, make it have high added value. On the other hand, in this study, by adding phosphogypsum slag and cement as curing materials, it also achieves the role of waste treatment with waste. As shown in the figure, Nanjing and others designed the granulated blast furnace slag, phosphogypsum, and calcium carbide slag as high-performance ternary curing without clinker. The results show that it has good working performance. It is expected to completely replace cement as a low-carbon cementitious material. This provides an effective basis for using phosphogypsum as a solidified material of rock fine in this study. Bansor et al. Studied the effects of pouring and compaction on the mechanical clay bricks. The results show that compared with uncompacted control bricks, the compressive strength, tensile strength, and flexural strength of the compacted test bricks increased by 79.43%, 42.42%, and 75% respectively. So the compaction process is a better method for preparing clay bricks. Combined with research experience of the above scholars, we choose phosphogypsum, slag, cement as curing material, mixed with waste rock fine according to a certain proportion, and prepare non-sintering environmental protection brick by compaction technology. It is used for the resource utilization of waste rock fine and phosphogypsum. Because the particle size of waste rock fine is fine and contains a certain amount of clay particles, which directly affects the related properties of rock fine-based brick. So it is very important to explore the influence of clay fraction and performance of rock fine-based brick. So we need to figure out 2 problems. The first one is to separate the raw materials with different clay fractions. The second is to discuss the changes of mechanical behaviors of waste rock fine-based brick. Below, I will introduce the results of experimental analysis on the influence of clay fraction. Firstly, the raw materials are prepared. According to the decimeter method and the Stokes formula three kinds of waste rock fine were obtained by static water sedimentation method. Then the chemical composition and mineral composition of the test materials are analyzed, and the results are shown in the figure. Among them, the chemical composition of rock fine is mainly calcium and silicon oxide, and contains a small amount of iron and aluminum oxide. The preparation method of the sample mainly includes the following processes. Firstly, dry powder is mixed and stirred evenly. Then is added according to the water-cement ratio of 0.15, and then stirred evenly again. Finally, the sample is put into a 50 multiplied by 50 millimeters mold, compacted by a press, then demolded and cured. After curing, the sample is analyzed experimentally. First of all, the strength test, as shown in the figure. After natural curing and soaking curing for 7 days and 28 days, the unconfined compressive strength of the sample is tested, and the strength of the sooty and clayey WRF modified sample decreases by 4.1% and 16.5% respectively. On the other hand, the strength of the sample also decreases greatly under the condition of immersion, among which the clay sample decreases the most, reaching 82.6. This shows that the original rock fine gradation is more complete in the process of compaction and accumulation. The structure is denser, and the limited supply of cementitious material makes the hydration more complete and the hydration products more. However, the strength of the sooty and clay samples is weakened due to the single gradation and the insufficient supply of cementitious materials. The stress strain curves of three kinds of samples after natural curing and soaking curing conditions are shown in the figure. The relationship between failure strain, deformation modulus, E50, and the UCS can be calculated by using the full stress strain curve. There is an obvious linear relationship between deformation modulus, E50, and the confined compressive stress, which can be expressed as the formula shown in the figure. There is no obvious mathematical relationship between failure strain and the confined compressive strength, and the failure strain is mainly distributed in 1% to 5%. The leaching test results show that the leaching amounts of phosphorus and fluorine elements in the samples are far lower than the contents in the standard, so they will not have a bad impact on the environment and have good environmental protection. The mercury injection test shows that the internal pores of natural WRF-based samples are less, and those of sooty WRF-based samples are larger, which is consistent with the previous results. The scanning electron microscope test results listed the microstructure of three kinds of the samples. It can be seen that the natural WRF-based sample has fewer pores and more hydration products, which is consistent with the previous experimental results. The number of pores in the sooty sample is slightly less than that in clay sample, but the pore diameter of these pores is larger, and the clay sample has more pores. Combining the above experimental analyses, we get the following conclusions. It shows that the strength of waste rock fine-based brick is mainly controlled by bonding and filling effects, among which the strength of sooty and clay WRF-based modified samples is lower than that of natural WRF-based modified samples due to gradation effect. In addition, it was noticed that although clay particles may participate in the secondary pozzolanic reaction to contribute bonding strength, they also possess superior absorption capability owing to the large specific surface area, which will absorb down the surface of cementitious materials and thus hinder the hydration reaction. In the future, we will put rock fine-based brick into the pilot stage as soon as possible and put it into practical application. Only in the actual application process can problems be found and then improved continuously. The above is all the contents of my report. Thank you all. If you have any questions, please email me.